So welcome everyone to AA228V, CS230AV, validation of safety critical systems. If you're here for that class, you're in the right spot. If you're here from a different class, you're in the wrong spot. And we promise not to judge you if you get up and leave now if you're in the wrong spot. That was definitely one of my biggest fears as a student on the first day of class. So my name is Sydney Katz. I'll be the primary instructor for this course, along with a super awesome teaching team, and we'll all introduce ourselves shortly. But first I want to jump in by just saying, so this is actually the first kind of quarter-long full class that I've ever taught, and I'm really excited about it. And so I thought kind of long and hard about what the first slide of the first lecture of the first class that I ever teach should be. And here's what I came up with. Yay! So yay for a couple of reasons. One, I'm just super excited to have this opportunity. I think like throughout my kind of entire academic journey, I've always really loved teaching and helping students understand concepts. And so I'm just really excited to have this opportunity. And also yay because I'm excited about the particular class that we're teaching here, which is validation of safety critical systems. So I think this is actually kind of one of the first classes of its kind. It's a new class, as you probably know. And I think kind of a lot of the skills that you'll take away from this class are going to be extremely useful and valuable whether you go into industry or academia, in a whole wide variety of domains. So I'm just really excited to share all of that knowledge and skills with you. So yay. All right. So with that, I'm going to jump in now and talk a little bit about the textbook that we're going to use for this class. So the textbook is called Algorithms for Validation. It was co-authored by myself, Mykel Kochenderfer, who's one of the co-instructors for this course, Anthony Corso, and Robert Moss. And so this textbook is actually the third textbook in a series of textbooks. They're all algorithms books. So if you've taken any of Mykel's other classes, such as AA222, or maybe last quarter you took AA228, you might have used one of these textbooks in the past. And the way I kind of see these textbooks fitting together is like this. So in the first two textbooks, we design stuff. So we design decision-making systems, we optimize them, and then once we're done with that, we come over to this textbook or to this class, and we check if what we designed actually works. So we check if it does what we intended for it to do. But ideally, we're going to find out in a controlled and safe environment, such as a simulation, instead of in the real world, unlike these people. So the one on the right is actually me. I can tell you that was from when I was an undergrad, so I hadn't taken any validation classes yet. I didn't know what I was doing. So there was no validation involved. I just kind of started spinning around a bat and didn't really know how dizzy that would make me. Definitely had no chance of hitting that piñata. Okay, so those were some fun systems. But in this class, we're mostly going to be focused on decision-making systems, and specifically decision-making systems that operate over time. So this could be something like a robot, an autonomous vehicle, an autonomous aircraft, maybe a financial system or a healthcare system. And in this class, we're kind of just going to wrap that all into this one component that we call the system. So in other classes, you may have learned to design intelligent decision-making systems like this. In this class, we're going to assume we already have that system, and now we want to check if it does what we wanted it to do. And to do that, we have to give it some sort of specification. So we need to write down something that tells us what it is we actually wanted the system to do when we designed it, and what do we want it to do when we deploy it in the real world. And so these are kind of the two main inputs that go into validation algorithms that we'll be talking about in this class. And what a validation algorithm does is essentially takes that system and specification and outputs some sort of information that tells us whether the system is satisfying the specification. So that information could be something like a failure analysis. So when does the system not satisfy the specification? It could be a formal guarantee. So that would be something like under a set of assumptions, maybe sometimes we can prove that a system will always satisfy a specification. It could be an explanation, so maybe we can explain why a system doesn't satisfy a specification or why it makes a particular decision. all the way to when we deploy the system at runtime, we could kind of deploy it with some online validation that allows us to continue checking if our system is operating as intended when it's out in the real world. And so we're actually going to discuss algorithms from all of these different categories throughout the quarter. And what I want to say here is just that there's not really one single algorithm that's going to do it all for us. So there's not one algorithm that we could just run it on our system, see that the results pass, and then confidently deploy our system in the real world. And instead, we really need to apply algorithms for all of these categories to sort of build a safety case. So you might be wondering why there's like these cheese-looking things on this slide. Essentially, the idea here is something called the Swiss cheese model. So maybe some of you have heard of this before. If you haven't, I'll give a quick 30-second overview of it. But the idea is basically just that all of these methods have different limitations or holes in them, just like the slices of Swiss cheese. But ideally, the limitations that these algorithms have, maybe the limitations of one algorithm don't line up with the limitations of another algorithm. As you can imagine, if we stack enough of them together, just like we're stacking the slices of Swiss cheese, then ideally we won't be able to see through any of the holes. And so we'll be able to kind of catch everything that other algorithms miss. And so the key idea here is just that there's really no silver bullet in safety validation. And instead we need to build a safety case for these systems. So like I said, in this class, we're going to talk about algorithms that kind of fit into all of those categories of methods. And so this course is a really good place to start to kind of give you that toolbox to be able to validate the systems that you design before you deploy them in the world. Okay, so hopefully that gets you excited to take this course. Let me just talk for a second about the plan for the rest of this lecture. So the course staff will introduce themselves. Then I'm going to do my best, if I haven't already, to convince you that safety validation is important. We'll talk about the validation framework that we're going to use throughout this course. So I'll introduce myself first. Here's kind of just like a timeline of my academic journey so far. So I did my undergrad at Washington University in St. Louis in electrical and systems engineering. And during my time there, I got to do some really cool internships. But one that's kind of a major highlight and particularly relevant here was at MIT Lincoln Laboratory. And that's actually where I first met Mykel. And also it was where I got to work on a system called ACAS-X. And essentially what it does is collision avoidance for aircraft. So this was kind of my first introduction to intelligent decision-making systems that operate in safety critical settings. And so really it's kind of what set me down the path for my PhD. So after I came here to Stanford, I'd heard how great Mykel was, so I was like really hoping he'd let me in his lab, and he did. And so for the next 5 or so years, I worked on the design and validation of safety critical decision-making systems. And specifically, my PhD thesis was focused on safe machine learning-based perception. So it's kind of like that video that I'm showing there. That would be an example of a perception system we might work on, where we basically have a camera that's mounted on an aircraft that's trying to detect other aircraft in the sky to avoid colliding with them. So then I got my PhD in 2023, and I've stuck around as a postdoc for the last year or so. And a large portion of my time as a postdoc was spent actually working on the textbook for this course. So I've been doing kind of a broad survey of the validation algorithms that are out there, and I'm really excited to share them with you. Okay, so some fun stuff. I used to collect bouncy balls. I have like jars of them at my dad's house. I never got my wisdom teeth, so that doesn't mean it's not that I never got them out, I just like never got them, period. They just never formed in my mouth. I was born in the same hospital as LeBron James and Steph Curry. If you're not a basketball fan, LeBron James and Steph Curry are like two of the best basketball players to ever live. I did not get whatever was in that hospital. I'm not the best basketball player by any means. And actually, to like really contrast that, I didn't even learn to ride a bike until I was 23. So if there's any of you out there that still haven't learned to ride a bike, there's still hope for you, no worries. I actually learned when I came to Stanford because there was just no other way that I was going to be able to get around this giant campus. But then I guess to contrast that again with some athletic ability, I used to jump rope competitively, and I was part of Stanford Jump Rope also for a few years while I was here. And that's a picture of me at Yosemite on our lab retreat last year, jump roping. All right, let Mykel.
All right, my name is Mykel Kochenderfer. I see a lot of familiar faces. Really happy to see you again. And I'll be having office hours by appointment, so feel free to send me a note. I'm looking forward to getting to know many of you, all of you actually. So I came to Stanford originally as an undergrad and stayed for a co-term, then went to the University of Edinburgh for the PhD. I went to MIT Lincoln Laboratory, which is a fantastic place to work and make lifelong friends. And then I stayed there for 7 years working on ACAS-X and airspace modeling and other areas. And then I had the privilege of coming back here in 2013 and starting the Stanford Intelligent Systems Laboratory, or SIZL. We've enjoyed collaborating with a number of different research sponsors, both government and industry. So I'm a Swiftie, and you probably know that if you took 228 with me. I guess we're talking about wisdom teeth now. So I got 5 of them, and I was a little loopy after getting them extracted. I like taking students on overseas adventures. The past couple summers, we've gone to India. This summer, I'm taking a group of 15 undergrads to Argentina. It's not too late to apply. I have had 0 bike accidents at Stanford, owed, I think, primarily to the fact that I treated as a POM-DP with some heavy collision penalties. I'm a 3rd-generation pilot, and yeah, really happy to be a part of this course, and also looking forward to your feedback on the textbook and your feedback on this course as well. We hope to offer it every year during winter quarter.
Okay, so that's course staff intros. Now I'm going to try to convince you that safety validation is important. So there was this teacher that told students that they could bring in a 3x5 cheat sheet for their test, but he didn't specify that he meant 3x5 inches. So one student took the liberty to then bring in a 3x5 foot cheat sheet for their test. And so this is an example of kind of a misspecified objective. So I'll just say robots and maybe some students will do exactly what we tell them to do, and we need to give them good instructions. And there's actually a name for this phenomenon, and that's called the alignment problem. And there's kind of 3 main things that can cause the alignment problem. One is an imperfect objective, one is an imperfect model, and then the last one is imperfect optimization. So I'll kind of go through these. So what we just saw with kind of the cheat sheet thing, that's an example of an imperfect objective. So the teacher's objective was to have students bring in a 3x5 inch cheat sheet for their test, but he kind of misspecified that and he just said 3x5. So that was kind of too ambiguous, and students could interpret that how they wanted. And so one student then brought in a 3x5 foot cheat sheet. Here's another really famous example of an imperfect objective. So the idea here is we had some researchers that were trying to train an agent to play this boat racing game. And they wanted to essentially train an agent that would be able to win the race. And the way the game is scored is just by kind of the score that depends on how many various objects or items you pick up along the route. And the idea is that a high score should win the race. So here's what actually ended up happening. Play this video. Okay, so this should probably look a little bit weird to you. It definitely doesn't look like a boat that's trying to win the race. And it turns out what happened is the boat kind of figured out, or the agent figured out, that basically if it was able to kind of crash into things at the exact right time and speed, it could kind of enter into this infinite loop where it just kind of collected those green turbo things, which gave it a really high score, forever into the future. So that's one way to maximize the score, but that's not what we as the designers of the system actually wanted it to do. So this is another example of an imperfect objective. where we told it to maximize the score, but our actual intent was to win the race. Here's another kind of interesting example, which I actually kind of tried at home. So many of you may use coding agents to help you write code that use like LLMs to complete the code you're writing. So this is actually in my VS Code. I just went ahead and typed in calculate women's salary, input a base, and then what you see kind of grayed out there is what it was telling me to complete the function with. So it was basically telling me to take the base salary, multiply it by 0.77 and give that to the women. And then I tried the same thing, calculate men's salary, input a base, and it was basically telling me to take the base, multiply it by 1.1 and give that to the men. Seems a little bit unfair to me. And this is kind of another example of a misaligned objective. So typically when we train agents like this, we're just training them to kind of complete the next token in a sentence or in a block of code. And there's nothing in that objective that necessarily says it needs to create fair code. So again, this is kind of a mismatch in objectives. Okay, the alignment problem could also be caused by an imperfect model. And so one kind of interesting example of this, which we mentioned in the intro chapter of the book, is this hedge fund called long-term capital management. So this hedge fund was created in 1994. And when it first came out, people were really excited about it. It was supposed to do super well. And at the beginning, it actually did do quite well. So you can see this kind of light blue line here. That shows the performance of the S&P 500 over the next few years of when the fund came out. And it's kind of just a good thing to like index performance of funds against. And you can see that this kind of dark blue line shows that the fund was like pretty significantly beating the S&P 500 for the first few years of its existence. But the problem was that the creators of this fund actually had kind of an imperfect model of the world in that they failed to account for extreme events. And so then when extreme events did occur, such as the economic crisis in Asia and Russia in 1997 and 1998, the value of the fund plummeted quite drastically to the point where it actually ended up requiring a multi-billion-dollar bailout by a number of banks. And that was to avoid essentially a global economic crisis. And what's kind of interesting about this example is that part of the reason the fund was so highly regarded was because it was created by some very highly regarded economists, two of whom actually won the Nobel Prize in 1997 for their work on the Black-Scholes model. And so if you're interested, there's actually an interesting book out about this called When Genius Failed. So that's an example of an imperfect model. And then finally, the alignment problem could also be caused by an imperfect optimization. So for example, here, maybe we have our objective perfectly specified. We know the model of the world, but we still need to then train our agent to do what we want it to. And so here's kind of what I typically think of with imperfect optimization. Maybe we have like a reward up in the right corner there. And what we would want an agent to do is essentially just kind of navigate its way to get this reward. But depending on the optimization algorithm we're using to train our agent to do that, it might not always end up doing that. So for example, if we have an algorithm that struggles with sparse rewards, so for example, maybe it just kind of explores the space all around, and if it never knows that this reward is here, then it still might not learn the policy that we want it to. Okay, so those are kind of three things that can cause what we call the alignment problem. If you're interested in learning more about the alignment problem, we highly recommend checking out this book here. But the reason that we're essentially talking about it right now is because the alignment problem is really what motivates the need for validation. And this is especially true for complex systems that operate in safety critical settings. So these are all examples that are mentioned in the book. On the left is a healthcare example where there was this radiation machine that, due to a software glitch, every once in a while would just administer a lethal dose of radiation to patients. So obviously that's not good. Many of you have probably heard about the Boeing 737 MAX incident, or multiple incidents that resulted in quite a bit of loss of life. And then you've probably heard about autonomous vehicle accidents in the news. And just what's kind of key here to note is that when these systems don't operate the way we intended them to, so when there is some sort of misalignment, those failures can result in very, very catastrophic outcomes. So loss of very expensive property or loss of human life. And so it's really, really crucial that we do validation in these safety critical settings. Okay, so are you convinced now? Many companies and regulatory agencies are. So for example, throughout my PhD, I did a lot of work in the aviation domain. That domain is extremely highly regulated, specifically in the United States by the Federal Aviation Administration, or FAA, and in Europe by the European Aviation Safety Agency, or EASA. And they basically specify all sorts of guidelines that you need to comply with in order to deploy something in the airspace. And so this is just an example of one of those guidelines that is kind of famous, DO178C. And it basically specifies what you need to do to deploy software on airborne systems. And these guidelines can be quite complicated or quite difficult and require lots of effort to comply with and show that your system complies with, to the point where there's actually even like full textbooks written just about complying with these standards. And then kind of what's interesting as of recent is now AI and machine learning are starting to become super popular. And we're thinking about what would happen if we were to put them on these safety critical systems, for example, like aircraft. And these regulatory agencies are very much thinking about that too. So both the FAA and EASA have released roadmaps of how they see AI and machine learning being deployed on these systems. But I think there's still kind of a number of open problems in terms of how we actually validate these systems to be safe enough to put on these very safety critical systems. So if you're interested, I think this is a really interesting area of research, and hopefully this class will give you some good foundations to kind of understand how to dive into it. Okay, switching domains to autonomous driving. So that's another domain that obviously cares quite a bit about safety. So for example, Waymo on their website, they have an entire section just devoted to safety, and they often release very detailed safety reports of their cars. Of course, gotta mention LLMs. So Anthropic, for example, which is a large LLM provider, one of their core research principles is safety and scaling. And you may have heard recently, a lot of people are interested in red teaming these LLMs, so trying to find inputs or prompts that cause them to misbehave. And I think this red teaming is actually quite similar, at least in concept and idea, to the falsification that we're going to talk about in this class. So hopefully this is also a good place to start for that. And these companies are hiring. So if anyone's looking for a job, this should hopefully give you some pretty good skills. I just kind of went on their websites, and if you search safety, there's plenty of jobs that are like literally just devoted to safety. But I think even if you're not going into a position that's like specifically focused on safety, this is a really valuable set of skills to have, because no matter what the thing you deploy in the world after you design it, you want it to do what you intended it to. Okay, are you convinced now? I hope so, because we're going to move on. Okay. So now I'm gonna jump into introducing the validation framework for this course. So I already kind of talked about how we structure validation problems. So we have a system, we have a specification, and then those go into a validation algorithm. The textbook that we'll be using is kind of structured in this way. So the second chapter is all about how we actually go about modeling the system, which we'll talk about in the next lecture. The third chapter is about how we can specify formally the properties for the system. And then the remaining chapters, which is kind of like the meat of the book and the meat of this class, is the validation algorithms that we'll get into. So just briefly right now, I'm going to kind of describe each of these components just so you can kind of get an idea of how everything's set up. So I'll start with the system. Okay, so there's lots of different ways to define a system, and you might define systems differently depending on like what class you're in or what domain you're in. In this class, we're going to say a system consists of an agent, an environment, and a sensor. And they fit together like this. So essentially, the environment keeps track of some sort of state of the world that's relevant to the problem that we're interested in. The sensor then observes that state and gives us an observation of that state. The observation then gets passed to the agent, which uses that observation to select an action to take. And then given that action, that environment will transition to a new state, and then this process kind of just repeats. Okay, and the way that we kind of more formally model each of these things is using probability distributions. And specifically, we use something called a conditional probability distribution, which we'll talk more about in the second lecture. But essentially, the idea here is just that for the agent, for example, given the observation that it receives, it has some probability of taking each action. So this represents the probability of taking action A, given that we received observation O. And we call this a policy. Once the agent has picked an action, it goes over to this thing we call the transition model, which essentially tells us, given the current state we're in and the current action that we take, what is the probability of transitioning to state S prime? And then that new state gets observed by a sensor, which basically tells us, given that we're in state S, what is the probability that we end up with observation O? So I'm going to try to make this concrete. I think kind of throughout the class, I'm going to do my best to kind of keep running examples going so that I can make all these things concrete. And one running example we're going to use quite a bit is the inverted pendulum. So here's a picture of it. Essentially the idea here with an inverted pendulum, if you've never seen it, so a normal pendulum kind of goes like this. Inverted pendulum is kind of flipped upside down. And the goal is basically to keep the pendulum balanced upright. And we can do that by applying torques at the bottom of it. And so we want to keep it kind of balanced, completely vertical. And so to represent the state of the pendulum, we're going to say the state is kind of its angle from the vertical, so this angle here. We'll call that theta. And then the other component of the state is its angular velocity, so how fast that angle is changing. And we'll call that omega. So that state will then go into our observation model for the inverted pendulum. We'll talk more about kind of what this distribution is in the next lecture, but essentially it's a multivariate Gaussian distribution that's centered at the true state with some covariance that kind of represents some amount of noise on the true state. So then we can sample an observation from this observation model, and we get something like this. So here we have the true state of the pendulum, which is like what's shown in white, and then the observation is kind of like that shadow there that's in the dark gray. And we'll call that theta hat and omega hat. That then gets passed to the agent. In this case, for the inverted pendulum, the agent is deterministic, meaning that it always takes the same action. And so the way we represent that as a probability distribution is just by saying that with probability 1, we take this action, and for all other actions, we take them with probability 0. For those of you who are interested, this is just a proportional controller, so we just multiply the components of the state by some values, and that tells us what torque to apply to the pendulum. You don't have to worry about knowing how to derive this or how to come up with this. There's other classes at Stanford for that. In this class, we're just going to give you the equations for all of these things. Okay, and then once we've selected an action, it goes over to the environment. And very similarly for the pendulum, the environment is deterministic. So with probability 1, we transition to this new angle and this new angular velocity. And then all other states have 0 probability. And then kind of same thing, there's other classes at Stanford that tell you how to derive these equations. You don't need to worry about how to do that. We'll always just give them to you. Any questions on that? Yeah.
So this model we're looking at continuous time system, since I see this delta t in the environment condition.
Yes, that's a great question. It does change things sometimes. In this class, we're going to focus entirely on discrete time systems. Good question. Okay. Okay, so you'll notice if you've checked out the textbook yet, the algorithms are implemented in actual code. So instead of pseudocode in the book, we actually use real code in a language called Julia, which we'll be getting familiar with throughout the quarter. So this is kind of a first example of a code block. What's really nice about Julia is that it's very, very human readable. So instead of writing in pseudocode, we can just write the algorithms in Julia, and they're basically just as readable. So all that's really happening in this code block here is we're defining types for the agent, environment, and sensor. And then we're just saying that a system type consists of an agent, an environment, and a sensor. Then, given this, we can actually go about trying to implement kind of this loop that's going on here as a function in code. So what we're going to do here is we're going to assume that we start in some initial state like this. So that's input to our function. And then we go to the next part of this loop where we use our sensor to produce an observation of that state. So for the pendulum, it's like that noisy observation I was talking about. That observation then gets passed to the agent here. And it uses that observation to pick an action. In this case, it's this torque here. And then that action is given to the environment, and we transition to a new state we'll call S prime. And then we just return what happened so that we have that information. Okay, so that's one time step. But you can imagine, if we want to keep going around this loop, we could continue to compute this over a number of time steps, all the way to some desired depth d. When we do this, it produces a trajectory, and we call this process a rollout of the system. So essentially, here's another function where it's called rollout. We take in our system and some desired depth d. And all that's going on here is we're sampling a random initial state, initializing our trajectory, and then for each step in the up to the depth d, we take one step of our system, look at what was output, just store that in our trajectory, and then set our state to be that new state. And then we just continue to do this until depth d and return the trajectory that we get. So here's what that looks like for the inverted pendulum. So I'm going to show a 20-step rollout, which ends up being 2 seconds long. So here's what it looks like. So you see we're able to balance the pendulum. And it's kind of nice to see those videos just to kind of get a physical understanding of what's going on. But in this class, we're going to actually look at a lot of plots that look something like this, where on the x-axis, we're showing the time step, or the time, and then on the y-axis, for the pendulum anyway, we're showing the angle of the pendulum. These red regions here, pretty much anytime you see a plot in this class with red regions, we just don't want the thing to enter into the red region. But we'll talk a little bit more about how we actually get these red regions when we talk about the specification. But here's essentially what it looks like if we plot the angle of the pendulum over time. So I turned this trajectory green because it didn't enter the red region, the pendulum stayed upright. Okay, that's the system. Now we need to say what it is we want our system to do. And we can do that with specifications. And in this class, anytime you see the Greek letter psi, that's what we're going to use to represent specifications. So one specification for the pendulum we've been talking about, for example, could just be do not let the pendulum tip over. Maybe for an aircraft collision avoidance system, it could be do not collide with other aircraft. Self-driving car, it could be something like stop when the traffic light is red. Maybe for a financial trading system, it could be don't lose more than $1 million if you have a lot of money to start with. Maybe for an LLM, it's something like don't produce harmful speech. And maybe if you're Mykel, it's don't use a pipe symbol instead of /mid when writing conditional probabilities in LaTeX. Okay. Mykel told me that I need to make jokes throughout this class to keep you entertained, which is my goal. But a lot of them might be jabs at him. Okay. So these are all kind of written in natural language. But for our validation algorithms, it's a little bit easier to specify them in a sort of formal, precise language so that our validation algorithms can understand them and do various things with them. So there's various languages that we'll talk about in this class. Maybe you've heard of linear temporal logic or signal temporal logic. If you haven't, no worries, we're going to talk about them in a few lectures. But essentially, these are the types of things we'll be using. And those allow us to translate kind of this natural language into a formal specification. So just continuing with the pendulum example, we need to define what exactly we mean by do not let the pendulum tip over. And so essentially what's going on here is we're going to define the pendulum tipping over as the magnitude of its angle exceeding pi over 4. So if it becomes greater than pi over 4 or less than negative pi over 4, or essentially anywhere in this red region, we're going to say the pendulum's tipped over, and we want it to stay in this green region. So there's a way to kind of formally write that down using a language called signal temporal logic, and it looks like this. So no worries if this looks like kind of just gibberish to you right now. It won't after a few lectures. But this is essentially what it looks like, and what this is saying is the absolute value of theta, or the angle of the pendulum, must always be less than pi over 4. And again, no worries if this kind of looks like gibberish. We're going to talk about what all this means in lecture 3. Okay, so that's the system and specification. And then these get passed to our validation algorithms. So let me talk a little bit about the validation algorithms we're going to discuss in this course. So the validation algorithms that we go through in this course, I've kind of separated into 3 main categories. The first is failure analysis, the second is formal methods, and the third one is other useful stuff. So for failure analysis, there's kind of some subcategories here. The first one is falsification. So the first thing we're going to do is say we have a system and a specification. We just want to find some scenarios where the system doesn't satisfy that specification. So we're just going to basically search for failures of the system. And so you'll actually get to try that out in the first programming project. After that, we're going to try to take things one step further and quantify the full distribution over failures for a system. And then after that, we're going to take that even one more step further and talk about failure probability estimation. So how can we actually estimate the probability of failure for a system? And you'll get to try that out in project 2. I'm really excited to kind of share those techniques with you because I think being able to estimate a probability of failure for a system is a very powerful tool. Because if we know a system's failure probability, we can potentially make very important decisions about whether it's safe enough to deploy in the world. Okay, so for formal methods, so these methods are basically kind of formal proofs under some set of assumptions that a system will always satisfy a specification. And so most of the formal methods we talk about in this class will be related to something called reachability, where we basically figure out what are the set of states that a system could reach over time. And if we find that a system can't reach any states that we consider to be dangerous, then we can say that our system is safe. So we'll talk about how to do that for linear systems, how to do that for nonlinear systems, and how to do that for discrete systems. And you'll get to try that out with the third project. And then other useful stuff is explainability and runtime monitoring. So I'm going to now just talk a little bit about each of these categories, kind of get you excited about what's to come. If any of this goes too fast or goes over your head, 1, feel free to ask questions, but 2, don't get too worried. We're going to spend a whole quarter kind of diving into all of these things. But I'll start by talking about failure analysis. And to do this, I'm going to use something called a Pluto notebook. So this is basically a notebook that we can use with the Julia programming language. And you'll be using them for your programming assignments for this course. But one thing that's really nice about them is it kind of allows us to do this sort of interactive coding. So it makes it really easy to kind of create these like interactive demos that I can show you during class. What's also really cool is if you're on the Stanford network, you guys can actually access these by just going to a URL, which is provided on the course website. And you can play around with these things as well, just online, which is pretty cool. Okay, so what's going on in this notebook? So this is the inverted pendulum system again. And okay, so essentially what's going on is the plot on the left there that says falsification, that's that first task. And so what I'm going to do is describe kind of a very naive method or very simple method for doing falsification, finding the failure distribution, and estimating the probability of failure. So here's our pendulum system. Again, we have that plot where we have time on the horizontal axis, the angle of the pendulum on the vertical axis, and we don't want our trajectories to enter into those red regions. So one way to do falsification is to just simulate the system a whole bunch of different times. Every time we do a simulation, we'll sample different values for the perception noise, and then sometimes those values might cause it to fail, basically. And so you can see here, we've simulated 30 trajectories or 30 rollouts, and we found a few failures, so our falsification worked. And then, if we want to find the failure distribution, kind of the simplest thing we could do is take all those trajectories we just sampled from our nominal distribution and just reject all of the trajectories that are not failures. So all this plot on the right is the same plot without the successful trajectories plotted. And it turns out that these trajectories are actually samples from our failure distribution. And so what's really nice here is that that's quite simple. It's a process called rejection sampling. But you can see already that we only have like 6 or so failures, so it's not very easy to really see what the failure distribution looks like just based on these numbers of trajectories. So that's already kind of one problem we're running into. And then another thing that's going on here in section 3 is the failure probability estimate. So you can see we had 6 failure trajectories. We simulated 30 trajectories total. So one really simple way to estimate the probability of failure is just to divide those numbers. And so we estimate the probability of failure to be around 0.2 here. Okay, so that's kind of the simplest way to do all of these things. But there is a point to the rest of this class, so I'll tell you why this way doesn't actually work super well. And so right now we actually have kind of a pretty high value for the perception noise. So this is essentially the standard deviation of the perception noise we're applying for the observation model. And if we change this, let's hope this works. Okay, if we change this, you can see that we start to have fewer and fewer failures as we make the perception noise lower and lower, to the point where we don't have any failures anymore, because our system has become so safe that if we simulate it 30 times, it just works every single time. So now our falsification has failed, we don't have any failure trajectories. Our failure distribution looks like nothing because we have no trajectories, and we're estimating that the probability of failure is 0. So the probability of failure is probably not 0, it's just that we haven't actually observed any failures yet. So that's kind of one way that the method breaks down. You might say, oh, okay, well, we'll just simulate a whole bunch more rollouts. And that is one option, and there you go, we did find one failure. But our failure distribution still isn't looking so good. We just have like now 2 trajectories in it. And so when systems are extremely safe and they have very rare failure events, this kind of very simple method of just simulating the system many times to do these tasks, it kind of breaks down. It doesn't work super well for us. But that's also the cases that we're often very concerned about, because for safety critical systems, they are designed to be safe, so they're already typically pretty safe. And they might have failure probabilities on the order of like 10 to the minus 9 or something like that. And that's going to require us to simulate many, many, many trajectories before these methods would actually give us valuable results. And so what we're going to talk about in kind of the failure analysis portion of this course is much more efficient ways to do this when we have systems with very rare failure events. So that was failure analysis. Now I'll talk a little bit about formal methods, specifically reachability. So here's kind of an example. We have kind of a very simple system here where it's just a 2D space that we're operating in. And then basically we're going to assume that we start with an x and y value that's somewhere in this purple square. And then we have a very simple transition model here, which is just that the next state is, or the x value for the next time step is the x value for our current time step plus 2. And then the y value at the next time step is the y value for the current time step plus 1. So before I kind of show the next animation, maybe you can just take a minute to think about what would happen to this square at the next time step. Okay, so hopefully you thought something like this, where you did some math in your head, and maybe what you envisioned was you took this square, you took all of the x values and you moved them over by 2, and then you took all of the y values and you moved them up by 1. So that's essentially all that's going on in these reachability algorithms. But sometimes the math becomes more complicated than the things that we can just do in our head. And so for example, here's the dynamics for the pendulum written out. And so you can see we have some kind of nonlinear terms here. We have like a sign in one of the equations. We have these like bounded potential perception errors. And so it's not quite as simple, but we can still do something like this. So we can still say, okay, we're going to start in some state that's inside this purple rectangle, basically saying that, you know, we start with some angle that's kind of near the vertical and some reasonable angular velocity. And then we can do some fancy math and figure out what states we could end up in at the next time step. In this class, we're going to talk about like what that fancy math actually is. And you can imagine that we don't want to do this just for one time step. We want to know like what are the set of states we could reach out into the future. And so what we could do is we could just keep repeating this process. So now we say we start in this set of states, do that fancy math again, and it tells us what states we could end up in next. Do that fancy math again, and so on. And again, we essentially don't want to end up in these red regions here. And so we see that like for all of our reachable sets here, none of them overlap with that red region. And so we can actually conclude, at least for this amount of time steps, that our system is safe. Any questions on that? You don't have to know how the fancy math works. That's something we'll go over in class. Okay. And another thing that's actually kind of cool is this is actually a really nice segue into neural network verification. So some of you may have heard of this. Essentially, it's understanding, given a set of inputs to a neural network, what is the set of outputs that we might have. And so let's go back and imagine that we have this scenario again where we're operating in this kind of just XY plane, and we start somewhere in this purple square. And then now our next state is actually represented by a neural network. So we take our current state, we pass it through a neural network, and that gives us our next state. And it turns out, like we often represent neural networks kind of pictorially like this. But if you think about it, they're really just big mathematical formulas like what we were looking at on the previous slide. And so it turns out if you just kind of apply these same concepts plus a few extra tricks, you can actually figure out what are the set of outputs that our neural network might have if we give it an input somewhere in this square. So if you've kind of heard about neural network verification but not sure how to get into it or not totally sure what it is, we're going to very briefly scratch the surface of it at the end of one of the lectures. Yeah?
So for all of these, you have an initial set, and then it seems like what's black and what's in the square is very clear. Do we ever go through methods where the initial distribution is stochastic, like random in some sense, and you're evolving the distribution of possible places rather than just like the set of places now?
Oh yeah, that's a really good question. We will talk a little bit, so it's kind of like probabilistic reachability in a way. We will talk a little bit about that when we talk about discrete reachability. So we'll have that for discrete systems. We don't currently have a lecture planned or a chapter in the book on kind of transforming probability distributions. Typically, we'll talk about ways to kind of just bound them. So if you, like one option is just to get most of the probability mass of your distribution in kind of your initial set and then go from there. But yeah, good question. Okay. All right, and then finally, some other useful stuff. So we have explainability. We're going to talk about a lot of different methods in this chapter. Just one example for the inverted pendulum. We'll talk about how we can characterize and explain the failure modes of the system. So it's not super exciting for the inverted pendulum. You just end up with one failure mode it's tipping over to the left, and the other failure mode it's tipping over to the right. But these methods would scale to more complex systems where it maybe isn't so obvious. And then for runtime monitoring, so I'm going to show you two videos right now. They'll play at the same time. They're going to be of an aircraft taxi system that's basically taking in images of the runway and using that to kind of navigate the aircraft safely down the runway. And so what I want you to pay attention to is in one of the videos, the taxi system is going to be working as intended, and in the other video, not so much. So here's what they look like. Can't tell if they're playing. Yeah, they are. Okay. So essentially what's going on here is in the video on the left, everything looks fine. It looks like the data it was trained on. And in the video on the right, we come to a point where another runway crosses over the runway that we're currently on. And this system had never seen anything like that in training, so it doesn't know what to do. And it kind of just confidently veers off to the side of the runway, not realizing that anything's going wrong. And so what we would rather do in a situation like that is have some sort of runtime monitor on the system such that when it gets to that point, it could say, hey, I'm uncertain, I've never seen anything like this before, and maybe it could just flag that or transfer control back to a human operator or enter some sort of safe mode that it has. And so don't let the fact that runtime monitoring is at the very end dissuade you from it. I think it's extremely important. when we deploy these systems, be able to kind of catch all the things we miss in these other offline validation techniques. Okay, so that's kind of the overview of what we're going to get into throughout the course. Hopefully that got you excited for what's to come. Are there any questions? Yep.
Sure, and just in practical terms, is there like a significant difference between Pluto and Jupyter notebooks?
They're very similar. One of the biggest differences is that when you run a cell, it will run any cell that also depends on that cell. And so that's kind of one thing to kind of get used to, but it makes it so that there's no like hidden state. So you can't have like some outdated code that wasn't run in a while that's like affecting things that you don't see. So that's kind of the philosophy behind it. There's a few other differences. I might be able to tell you more about it if you're curious. Yeah.
Projects in Julia?
Yes. Yeah. I'll talk a little bit more about that in the logistics. Okay, so yeah, maybe let's just get to the logistics here. So here's all the things I want to go through. Okay, so main resources for this course. Basically, everything I'm about to tell you about all these logistics you can find on the course website. I would recommend just bookmarking that for the quarter. Course discussions will be on Ed. You'll submit assignments on Gradescope, and these lectures are all recorded, and you'll be able to access them on Canvas. If you're having trouble accessing any of these, let us know on Ed. Obviously, if Ed is the one you're having trouble accessing, you can't tell us that, so you can email me, and we're happy to sort that out for you. We might just have to like sync the roster again, so do let us know if you're having any issues. Okay, so the schedule for the course, you can access it by clicking that link once I post these slides. It'll also be, it's also linked on the course webpage. So here's what the course webpage looks like. It's got lots of good stuff on there. Here's what the schedule looks like. So all assignments are going to be due on Fridays at 5 p.m. Pacific time. So anything you see in purple there on the schedule is an assignment that's due. There's basically something due every week for the rest of the quarter, except for this week. And then the other thing to note, I've put kind of the readings that go with each lecture on the schedule, along with some advanced topics that won't be on the quizzes, and also may or may not be covered in the lectures. It's up to, we do recommend you read the book. I'll stress that a few more times. But it doesn't matter to me if you read it before the lecture or after the lecture. I know some students like to read it before to understand the lecture better. Some like to read it after. Whatever fits your learning style is totally fine. Okay, lectures. So if you're here, you already know that they're Tuesday, Thursday, 1:30 to 2:50 in this auditorium. Like I said, the recordings of the lectures will all be posted on Canvas, so you do not physically have to be here in person. But with that said, please come if you can. That's my best puppy dog eyes to say please come. I'm going to be doing my best to really make the lectures worth your time, so I do hope you'll at least watch them. That's my dad's dog. Her name is Emmy. Essentially, I would just prefer to have an audience. So if you can come, you're available at this time, I'd really appreciate it if you could be here. Okay, one important note that I already kind of said, the main source of notes for the lecture is the textbook. So I will have slides. These slides will all be posted with any annotations that I write on them, so you don't have to worry about writing stuff down if you don't want to. But the main source of lecture notes is the textbook. So the slides are really just aids for me to kind of explain all of these concepts to you, but it's really important that you also are reading the textbook. Yeah?
Prior to class?
Yeah, I can do that. I'm making these lectures as we go, so I'll do my best, but I could definitely get them up at least right before. Yeah, thanks for asking. Any other questions? Okay. So yeah, like I said, you can access these slides. There's a Google Drive that I linked on the course webpage. And then any of those like notebooks I showed, like I showed earlier today, like I said, you can access them online, you'll just be able to like play around with the sliders. If you want to actually play around with the code that's in them and see the code that's in them, there's also a public GitHub repository that you're more than welcome to check out, all linked on the website. Okay, so the textbook for this course, which you said, is Algorithms for Validation. This is a new book. It's actually still in preprint mode, and so you'll have to access it as a PDF online. You can access it on that website there. We've tried our best to get it in the best shape that it can be in, but there will probably inevitably be some bugs that you find. So let us know if you do find bugs. You can post on Ed, or there's other ways to submit them. And if you do find a bug, we'll actually add your name to the acknowledgements of the textbook. And if there's lots of bugs that you find, we'll take the top 5 contributors of bugs to lunch at the faculty club with the textbook authors. So some incentive to really scrutinize it. Okay, grading. So if you've taken any of Mykel's classes in the past, like AA222 or AA228, it's structured very similarly. So there will be some projects, some quizzes, and a final project. One maybe thing to note that's a little different. So quiz 0 and project 0, they're actually going to count for 1% of your grade because we do actually want you to complete them. So it's not optional like it has been in other courses if you're used to that. And those are due a week from Friday. And then one thing to note, if you're taking the course for 4 units instead of 3 units, you should have the option. You're expected to spend an extra 30 hours on the final project, because that's the kind of expected time spent difference between taking something for 4 versus 3 units. Okay. Quizzes will be all on Gradescope, so you can take them remotely from anywhere. So if you're not going to be here on a quiz day, no worries, you just need to be somewhere where you can access a computer with internet. They're timed quizzes, but you can take them anytime within a 24-hour window. And so that window will start at 5 p.m. on Thursday and end at 5 p.m. on Friday of the week of the quiz. I'm going to talk about a late policy in a couple slides. That late policy does not apply to the quizzes. So all of the quizzes are due at 5, like that 24-hour window ends at 5 p.m. on Friday. Okay, and just so you know, the late policy does not apply to the quizzes, and the late policy does not apply to the quizzes. The late policy does not apply to the quizzes. The late policy does not apply to the quizzes. If you're ever wondering when anyone would ever use those ridiculous keynote animations, there you go. Okay, so projects. There's 4 projects, although project 0 is much more lightweight. So project 0, like I said, this is actually required, and we'd like you to do it so that you can get it set up with the environment that we're going to use for the projects throughout the rest of the course. We don't expect it to take you long, but we do recommend that you start early, especially if you're not familiar with Julia or you haven't used it before, just so that you have maximum amount of time to like get help from us or from the course staff if anything goes wrong or you need anything. And the other projects should be really exciting, emphasizing different aspects of the course. All projects will have an auto-graded code portion and a write-up portion. You'll submit both of those separately on Gradescope, except project 0 does not have a write-up portion. You just need to submit the code. So like I mentioned, the projects will be using the Julia programming language in these Pluto notebooks. If you're not familiar with Julia, no worries. One thing that's nice about Pluto is it kind of handles a lot of the different things like package management and whatnot that Julia has. It kind of handles all of that for you. So you should hopefully be able to just kind of like open the notebooks, follow his steps. He made a really nice video of how to get everything set up and just kind of jump in. And then these are kind of on the right here is what the Pluto notebooks look like. They'll just be places where you need to fill in code. So our goal here is really to have you be focused on the algorithms and not like the syntax of the code you're writing. Of course, you need to write code that works. But we really tried to make this kind of as smooth as possible for people that are not coming from a Julia background. And we're also here to support you if you need any help. Okay, if you've taken any of Mykel's classes in the past, you might be used to having a leaderboard. We're going to do the same thing in this class. So projects 1, 2, and 3 will all have a leaderboard, and the winners will get a prize, which will likely be lunch at the faculty club with the course staff. I will note, though, we've kind of made it so that most baseline algorithms will pass the programming projects. So your position on the leaderboard does not affect your grade at all. You just need to pass the auto grader. And then the leaderboard is kind of an incentive to dive deeper into the algorithms for those who want to. All right, so this late policy I was talking about. So all assignments are due at 5 p.m. on Friday, but there is a 72-hour no questions asked penalty-free extension that will be applied automatically. So you don't even need to ask us about it. And here's how this works. So I know all of your brains just went to, okay, projects are due at 5 p.m. on Mondays. Kind of true, but I do want to say one thing here. So let's imagine a scenario where it's Thursday night, the night before your project is due, and then you just spilled Coke or like coffee or something like all over your laptop and nothing's working. This is okay, because now we have a 72-hour extension where you can complete the project and figure out the laptop situation. But now, let's imagine instead that it's actually Sunday night and you just spilled coffee all over your laptop. This is also okay because you've already completed the programming assignment because it was due on Friday, okay? So that's how this extension works. So the idea is if you spill coffee on your laptop Sunday night, we will not be granting an extension. If you spill on your laptop Thursday night, you already have this extension. You don't even need to ask us. That said, we're not heartless. If we understand life happens and you have other things going on outside this class, if things do come up and you feel like you need more than that 72 hours or something goes wrong, you can still reach out. Don't hesitate. We want to make this a good experience for you. Okay, and the late policy does not apply to quizzes. And then just another heads up, we will cap the leaderboard on the project at 5 p.m. on Friday. So if you are interested in kind of maximizing your score on the leaderboard, you will not qualify if you submit past Friday at 5 p.m. Okay, so the final project, this is a way to kind of dive deeper into one or more of the topics in this course. Hopefully with a topic that kind of is exciting for you, maybe it relates to your research or what you want to do after you graduate. We're happy to help you kind of come up with topics. There'll be various kind of milestones throughout the quarter for the final project so that we can make sure you're kind of staying on pace. We're here to help you. If you're having trouble coming up with a topic, maybe if you took AA228 in the past, hopefully for that final project you designed a decision-making system. So maybe you could think about trying to do some validation on that system. Of course, that's not required. You can do it on anything you're interested in. And if you want some help brainstorming ideas, definitely stop by any of our office hours. And I think I didn't put it here, but you can work in groups of up to 4 on this project. 1 through 4, any number is fine. Okay, the best way to reach us is on Ed. We'll be monitoring that and trying to get back to you in a timely manner. If the question you're asking would benefit the rest of the class, it'd be really great if you could make that post public. You're allowed to post anonymously. I know that kind of helps get rid of some of the intimidation factor sometimes when asking questions. So please do ask questions if you have them, and you can be anonymous to your classmates if you want. That said, you can also make private posts as well. So if you're asking about something that might like give away an answer, so maybe you have code, please do make that private. And also if you want to ask about any like sort of accommodations or special circumstances that are going on, you can feel free to make a private post to the course staff. Okay, office hours, they're all on the course calendar. Some are in person, some are hybrid. You can come see us. And yeah, if that time doesn't work, if all the times don't work for someone, feel free to contact me. We can set up some other time. Okay, and then just a few miscellaneous things to wrap up. Please do give us feedback at any time. So this is a new course. We want to know how we're doing. We want to make this as good of an experience as possible for all of you. Yeah, so like I said, this is a new course. We've done as much offline validation as we possibly can to make sure that you have a good experience. I know it's new, but I want to make sure that it's not on you guys to debug this course for us. So we're doing the best we can to make it run smoothly. But something might go wrong, and so we do know that runtime monitoring is also important. So please do give us feedback, and we'll do our best to incorporate it throughout the quarter. We will be using the high-resolution course feedback. So some of you, every few weeks, will receive a survey of how things are going. Yeah, we really appreciate if you can fill that out, just for our own sake of making the course as good experience as possible for all of you. Okay, that's it for logistics. Are there any other questions on the logistics of the course? Yep.
It's a first time offering where there'll be like practice quizzes and stuff.
Oh yeah, good question. I'm making exercises for each chapter of the book. My goal is to have the exercises that would correspond to a particular lecture posted before that lecture. So the chapter 2 and 3 exercises are already posted. You can access them on the course webpage. That's the best way to prepare for the quizzes. All right, so that's everything for today. TLDR, in case you somehow slept through this entire lecture, validation is interesting and important, and this class will give you valuable skills, so get excited. Get started on Quiz 0 and Project 0. I don't know if I really said much about Quiz 0. It's also 1% of your grade. It just helps you kind of learn some of the logistical details of the course. So it'll ask you things like, does the late penalty apply to projects? Late policy apply to projects or quizzes? So make sure you do that. It should not be stressful or anything. You can submit it as many times as you want until you get 100%. We just want you to get used to submitting things on Grayscope and understanding the course policies. So Quiz 0 and Project 0 are due a week from Friday, so get started on those. Yay! We'll see you guys on Thursday.